Okay, shall we start? Ready to start?
Ready, teacher. Teacher, now your audio quality better already.
Is it?
Yeah.
This is an old laptop, but
No, but the audio quality now better already.
the new one is some problem. It's
Oh,
very slow to download, and I'm having problems. So I'm taking it sometime next week to go and the computer check up. It's take a long time to download and save also. Sometimes me behaving funny way. Okay, let us start. Let us start. Okay, let's look at sources of sound wave, how the sound is produced. Right, 21.2 syllabus wise sources of sound wave. Right, that one we have gone over that. Right, under sound wave in string. Right, so refer to that. Topic 20. Determine the frequency of sound wave produced by different modes of vibration of standing wave along the stretch string. E. Describe the appropriate diagram, the different modes of vibration of standing wave in air column. Calculate the frequency of sound produced, including determination of and correction. Okay, so we are just going to do this one. E. Right, so there are various instruments. Okay, your book mentioned a flute. There's a flute. There's a trumpet. Right? Remember, we are always looking at idealized case. Ideal case. Right? We don't want to look at complicated case, even though this may look complicated. Right? So these are all the different sources of sound. Vibrating string, we have done that. Guitar and piano. Right? That's a piano. Right? These are different form. To me, it looks like guitar, but they are called different names. Okay. Right? These are air column, vibration, air column. Right? Now we can see this in some church or some hall, especially for for music con for music concerts. Right? You will see this type of tube there. Wind instrument make sound by making the columns of air resonate. Right? We use the word resonate because the each tube of a particular length will produce sound when a fixed frequency is sent on it, not other frequency. That's why we call resonance. Just like force vibration, right? If you the string is swinging with a particular frequency, for it for resonance to occur, you you apply a force oscillation. Right? Force oscillation means that the frequency of the applied force is periodic, same as the frequency of the oscillation. That's why we call it resonant tube. Right? It only makes sound for a particular frequency or integer multiple of the frequency. Right? Or we can also have different note. Right? A bottle air filled with water of different level. Right? You can blow air or cross it, it will have a sound if the frequency of your air blow is the right one. Or we can hit the tube, it will give you a particular sound. Or we can study a more complicated one, okay, which is just for your information, Kun tube. Okay, let's look at standing wave in pipes or tubes. Right? Pipe or tubes are the same thing. Some book will call it pipes, some will call it tubes. Page 89 in your book, you can refer to that. Right? This is your pipe or tube. Pipes or tubes can be classified as open or closed. You can call it closed or open pipe. Wind instrument, for example, flute and trumpet, produce sound using vibrating air column. Flute, trumpet is the air column to produce the sound. In open pipes, both ends are open. These are open, both ends. So we call it open pipe. Right? This one end closed. We call it closed pipe. One end is closed. Pipes or tubes can be classified as closed or open. Yes, you said sound wave is sent from one end. Yeah, usually we send it at the open end. This one can be this end or that end there. This one is only one end. The wave are reflected at the other end. This one, if we send it from the left, send it to the left. Remember at this part there, there's a boundary there between the pipe and the free air that can move. So it will be reflected back. Same thing, you send the progressive wave, progressive sound wave to the end there, it reflected and then it return. Incident and reflected wave interfere to produce standing wave. Important. We produce standing wave by two progressive wave, one incident, one reflected. They interfere constructively. Then we hear a loud sound. Note, at the node is obtained at close end where disruptive interference occur. Close end, node. Just remember that. Don't need to ask why. Right? We don't want to go to detail on that. Antinode is obtained at the open end where the constructive interference occur. Open end, antinode, open end, antinode. This is also antinode there. You can think of antinode because it can vibrate freely. The particle there can vibrate freely. No constriction. Where this one is restricted. That's why it has to be a node. Open pipe. Right? I intentionally choose open pipe because it's related to your string. Right? Remember, that's your wave. Right? Remember, from crust to another crust is a wavelength. Right? From crust to a trough is half a wavelength. Right? From a zero to a crust is a quarter. Right? Or from a zero to a trough is also a quarter. That you must be able to recognize. Right? Or from zero to another zero, displacement is a half a wavelength. Okay, any comment? That one you must be able to recognize. If not, you will have problem. Okay, if not, let's carry on. Okay, that's your wave. Right? You can see freehand is difficult. Not that well done. The first one is always called the fundamental mode or fundamental frequency. We are looking at open pipe, both ends open. How to draw? The first one, right? Open end. The first one is from, remember we say antinode. So this is antinode. So the simplest one is from here to here. Right? You can draw that. Then cancel that one off. Cancel that one off. So that's the first fundamental mode of vibration. How the sound can be formed. So antinode at the open end. And then the simplest one is a node at the center. Okay, so you should be able to recognize this is a particular wavelength. Right? Your book will call it lambda naught, but I call lambda 1 easier. Right? Just identify it as a wavelength. This is half a wavelength. Half a wavelength equals to L. Take the 2 across there, lambda 1 is 2L. Right? Frequency is speed divided by lambda 1. Right? And your V equals to over 2L. Right? Remember, the speed, okay, forgotten, let's just review that. Where is it? Where is it? Where is it? Where is it? Where is my formula? Okay, there's a formula. Right? The speed is constant for a particular tube. Right? It depends on the atmospheric pressure and the density of atmospheric pressure, which I didn't write for you, but anyway, it depends on the temperature. Temperature doesn't change. If a particular gas that we use, air is constant, this one is the same, it doesn't change. So the speed is constant. Right? Just to refer to you. Okay, so the speed is constant. Just to stress you, the speed is constant. Right? Speed divided by lambda 1 will get your F1, the first frequency, or we call fundamental frequency, or first harmonic. So it's V lambda 1 is 2L divided by 2L. Right? So that's what we have derived. So the next one, we just the same thing. Right? Open end, antinode, open end, antinode. So that's the next one that we can have, open end. So you should be able to draw that. Right? Remove the others. So that's how it looks like. The length of the tube is L. So this is the, let's look at one side when you want to calculate your wavelength. This is a different wavelength from previously. So we call it lambda 2. Label all your antinode. Right? And then your node is here. That's your node. So lambda 2 equals to L. Okay. That's your one wavelength. Cross to cross. Then you want to relate to lambda 1. Right? L. L, you just take it into, take a 2 over there. So it's half lambda 1. That's how it's related. F2 is the speed divided by lambda 2. So lambda 2 is L, so it's V over L. Right? Refer to your note. Refer to your note. Right? Then this one, V over 2L. We take the 2 across there. V over L is F2. Okay, so we can call that 2F1. Okay, let's just summarize that. Okay, that's what we get for the first one. Fundamental frequency. Right? This one we call the first overtone or second harmonic. Harmonic we count from the top. Fundamental we call it first harmonic. Second harmonic. Third harmonic. Oh, this one is second overtone. Okay, so we have derived these two formula, and then we want to see, is there a general formula that we can write? Right? For Fn, we can see that this F1 and then F2 is related to F1. So we can try the others. You can try yourself for this one. Right? So we can see that for Fn, n times F1. Right? F2, 2 times F1. Where n is 1, 2, 3. See? Right? Lambda n is lambda 1 divided by 2. If it's lambda 2. Lambda 2 is lambda 1 divided by 2. So it's lambda n is lambda 1 divided by n. Right? You can remember that formula if you want to. If not, you can derive it. Okay, any comment? Anything not clear?
So far, okay, teacher.
Okay, let's just summarize it. Right? Same. The formula for standing wave in open pipe is the same as in string. Right? Let's go to closed pipe, page 85. Okay. First one, we call it fundamental mode of vibration or first harmonic. Right? As I said, this is the node, this is antinode, node, antinode, the simplest one. Right? Show how the wave can be formed. Closed end will be a node, open end, antinode. Length of tube, L. Fundamental frequency or fundamental wavelength. Right? Remember, this is 0, this is the crust, so it's a quarter. Right? Quarter of a wavelength, we call it lambda 1. You want to call it lambda 0, call it the first one, lambda 1, first harmonic equals to L. Right? Take the 4 across there, we got lambda 1 for L. Okay? So F1 equals to V or lambda 1. V is constant. Lambda 1 is 4L. So F1 is V over 4L. Right? Just now it was V over 2L for open pipe. Okay? We call open and closed pipe resonant pipe. Each length of pipe will give a loud note when we place a sounding tuning fork of the appropriate frequency. That means for this particular length, using this frequency, we will get a loud sound. Other frequency, slightly more or slightly less, we will get a loud sound. Right? That's why we call it resonant tube or resonant pipe. Right? We force the pipe to give a sound. Just like we force the oscillation to oscillate. Force oscillation. Okay, so you should be able to draw, same the wave. Right? Look at the wave. You want the zero, start drawing here. Right? And then the simplest one is a maximum or antinode here. So that is the others you can cancel off. No, right? So that's your fundamental. Then the next one will be not here. Right? This one will be here. Okay, so the first one has a particular length. The second one, right? And the wavelength is a quarter lambda. Right, call lambda 1. Then the next one, okay, remember this is a quarter lambda. I'm just stretching with you so you can remember. Right? So the next one is from here to here. Right? You can see 3 quadrants. Second overtone. Right? We don't call it first overtone because we will see that one is missing. But don't be too stressed up. Know that how to get the formula rather than try to stress if the different book will call it differently. And remove the other part. Right? So there's a second overtone, not the first overtone. Right? This is the third harmonic. Right? You can redraw that. Right? We have got our F1. Second overtone. Right? Our third harmonic. That's how we can draw that. Okay. This is half lambda. Right? You can focus on the top one. And the bottom one here. And this is from 0 to a maximum. So it's a quarter lambda 3. Right? So add it up is 3/4. And no antinode. Right? This is antinode. This is a node. This is antinode. Okay. So your L is the length equals to 3/4 lambda 3. Then take your 4 and 3, 4 across there and 3 down, then you get lambda 3 is 4/4 L. And F3 is V or lambda 3. Lambda 3, replace that. Right? Multiply by 3 here, multiply by 3 here to get rid of the 3 here. Okay? Cancel the 3, so you get 3V over 4L. Okay with that? Okay. Right? V over 4L. V over 4L is F1. This is 3F1. What you want to relate to the first one, the fundamental frequency. F2 is missing. Right? There's no F2. Right? You can summarize that. You can try for your exercise. You can try this one. Get the general, get the formula. Right? You can call that one lambda 5. Okay, just summarize for you. There's your fundamental wavelength or fundamental frequency. Then the second overtone or third harmonic. Right? We'll just derive that. Right? Frequency F3 is 3F1. Right? And we want a general equation. Now, of course, you can try the second one. It will show you the general equation. Right? And F1. N is odd. Okay, that's different. Previously, all numbers, all the whole number. Now, for closed tube, we want the odd one. I think your book do it slightly differently. So your choice, which one you want to reduce. Right? Lambda n, you can look at lambda 1. Right? Lambda 1 is 4L. So lambda 3 is 1/3. Lambda 1, there's a 3 there. We divide by 3. So if there's an n there, you divide by n. That's what we are doing here. Right? Remember, n is odd integer. If you use frequency, is F1 times n. If you use wavelength, the first one, the fundamental wavelength, divided by n. Okay, so we can compare. Summary, right? String at the fixed end will be your nodes. Open end. Open end is your antinode. Close end is your node. Antinode at open end. Right? Right? At open end is antinode. Fundamental wavelength is 2L. Open pipe and string the same. Close pipe is 4L. Okay. Fundamental frequency is the same as for string and open pipe. Right? This is for your string. This is for your open pipe. Right? You should be able to draw this simple thing. And then this one is for your close pipe, V over 4L. Okay, so general equation is the same. For open pipe and string, the same thing. Right? For closed pipe, slightly different. This is odd. 1, 3, 5, 7, all that. Okay, same formula. Same formula. Right? Same formula. Experiment to determine the speed of sound. Right? We can use a burette. Right? Or we can use a tube. Right? Here's a burette. This is your, right, to study pressure difference. Right? There's your reservoir. So we can use a tuning fork where we know the frequency. Right? Note the frequency of the tuning fork. That's the first thing. Sound it and place at the brim of the tube. Right? At the top there. Right? We just hit the table with the tuning fork. Then it will vibrate. It will give a particular frequency. Right? If you put near your ear, you can hear it. Too far cannot because the sound is very soft. Adjust the reservoir. Adjust this reservoir. You can put it down to increase this length. Right? So you start by raising the reservoir so that this water will fill the tube there to the top there. And then you move it down until you hear the first sound. Note the length of the tube. We call this one L1. Then after that, sound it again, repeat it. Right? Repeat the above procedure. Adjust again now. Right? From that one, L1, adjust it again until you hear a loud sound. Note the new length of the air column, L2. Then determine the wavelength. And then speed of sound is right, V times equals to F lambda. F is the frequency of the tuning fork. Wavelength is what we calculate. We will show you the calculation. Right? You can use a burette where this is your tuning fork, this is your L1, and then this is your L2. L2 subtract L1 is given you. Right? This is one of your worksheet. You have tried that. Right? So this is you should be able to draw a quarter wavelength is L1, Remember the end correction. It doesn't vibrate at the top there. It vibrates slightly. The end note is slightly above. That's why we call end correction E. Same thing as this one. Right? You should be able to draw. The second one, this is the antinote. This is a note there. There's a note there. Then you should be able to write the equation. Right? We use the same tuning fork, same frequency, same wavelength. So we have to adjust the length. Okay. So E is called the end correction. That's the antinote is a distance above the top of the burette. Right? Not exactly at the top there because it can vibrate. You want freedom. You want to be restricted. So 3/4 lambda. Right? This is 3/4, same wavelength that we use by 3/4 of a wavelength. And then this L2 plus your end correction. So we can subtract 2 minus 1. Right? 2 minus 1, 3/4 minus a quarter wavelength. We got half a wavelength. E and E will go off. So L2 minus L1. Okay, so that's why we get this formula. Then we can calculate our lambda. Right? We cannot use this to calculate our lambda because of the end correction. Okay, any questions so far? Okay, if not, let's carry on. Vibration of air particles in standing waves. Okay, let's just look at that. This is our open tube, first harmonic. Sound wave, remember, is longitudinal wave. First harmonic shows the displacement, distance graph. You can interpret this graph as distance, displacement, distance graph. You can either look at the red one or the blue one. Displacement of sound wave is horizontal, remember, for longitudinal wave. Taking upwards and to the right as positive. The arrow shows the displacement of a particle of the air either at the point either or pointing to the node or away from the node. This is the one. Right? This is positive. So these are all positive, different particle. This particle is larger amplitude. This one smaller amplitude. Right? This one smaller amplitude, small. Right? We look at the blue one, same thing here. This one is smaller amplitude, but the node there is not moving. This one, amplitude of vibration smaller. This one largest at the end, open end there. Or we can look at the red one. Right? And remember, we have said the particles, right, to the node there is all particles moving to the node there. Or if we look at the red one, same thing. The red one is negative. Negative. Right? Larger amplitude at the open end there, larger amplitude still. Same here. The red one is positive. The positive is moving to the right. Positive one is moving to the right. At the end one moving to the right. Yep. I heard you trying to asking something. Speak a bit louder. Okay. Ken? Okay. Can't hear you.
Where are teacher? 1 minute. Okay.
Okay. Let you absorb. Right, but here to interpret and draw the graph.
Okay, so first harmonic means they use the displacement distance graph, and then we are trying to tell the displacement of the sound wave
The
is
displacement
horizontal.
graph is
Yes.
how the particle is vibrating in the tube. You look at
Left
the blue
and right.
one, that's the blue one. You look at the red graph, that's how you get the red graph. All of them moving away from the node. This one, all of them moving towards the node. They are vibrating, right? They are changing. This is just for a particular instant, that's all. Okay,
Okay.
Right? All arrows point to a node or away from it. Right? Vibration of particle in a closed tube, the same thing. Right? Here is vibrating, smaller amplitude. Here is larger amplitude. Okay, at the closed end is stationary. Right? Sound wave, remember longitudinal wave. Mode of vibration can be taken as displacement distance graph. This is a displacement distance graph. At the node, the particles are stationary. It's not moving, not vibrating. Okay, so you can draw for the others yourself. I'll just include it in for you. Right? Sound wave, remember, is longitudinal wave. Mode of vibration can be taken as the displacement distance graph. So you can either look at the top one side, look at one side, or look at the other side. Right? We combine the two sides, then it's vibrating. That's why you show your two arrow there. Right? Pressure variation. Right? This is your displacement distance graph. Right? You want to look at pressure variation. That's the pressure variation. Right? Close end pressure antinode. Right? Close end, all the particles are together, so it must be high pressure. Open end, they are antinode, a lot of vibration, so the particles are at lower pressure. Right? So close end, pressure antinode, highest pressure. Open end, pressure node, lowest pressure. Right? That's how it completely different from your displacement of the air particle. Okay. So that is your pressure node, pressure antinode. High pressure, low pressure, zero pressure, or atmospheric pressure. And essentially know how to get the first one. Then the others will follow. Just remember this graph, how to get this graph, and then know. Antinode, there will be a node there. A node there, there will be an antinode for pressure. That's all. Any comment? Anything not clear?
Not clear, sir.
Okay, if it's clear, let's carry on.
No, sir, I don't understand this part, sir. What is it trying
You
to
understand
tell?
what?
The whole thing. I mean, I'm trying to understand it, but then kind of complicated.
Okay, we are just looking at that one, that's all. Right?
Okay.
This will be high pressure because all the particles are not moving. All these particles are moving towards that. This one, all the particles are vibrating at large displacement, so the pressure will be low. That's all. Right? As we have tried to explain to you previously. Yeah. This will be high pressure. This part will be low pressure because they are vibrating away, either in or out. So the low pressure, where all the particles are going towards the node, it will be high pressure. So that's how we are doing. Oh, is it not obeying me? Okay, so you just need to know that is for your closed pipe. This is high vibration antinode. This is your node. So for high pressure, you just remember where this is large displacement, low pressure. Yeah, low pressure, the mostly pressure. Where the particles accumulate, high pressure, that's all. Then the others will just follow. Same thing. Just know how to read. Right? Antinode, this become atmospheric pressure or low pressure. And the particles gather, this is high pressure. That's all. As long as you know how to draw this displacement distance graph, you should be able to draw this one. You just follow from here. Remember these two things. Close end is the pressure antinode, highest pressure. Right? Opposite to your displacement distance graph. That's all. Don't know why you have problem understanding. Just remember these two things. That's all. And the particles are together at the close end, high pressure. The open end is vibrating with large amplitude, antinode. So the pressure will be the lowest. That's all we need to remember. Then draw, that's all. Yeah,
Yeah.
that's the best I can go over with you. But if you still cannot, you have to think over it. Okay, so that is for standing wave in closed tube. Right? Don't let that confuse you. This is too many. We are looking at the simplest one good enough. Right? Remember that, that's all. Right? Remember for standing wave in open pipe, that is your displacement distance graph. That's your pressure changes. Okay. So we have completed. Let's try some question. Before we end, let's try some question. Make sure you know how to solve the problem. Where is my checkpoint? Okay,
Teacher, so
checkpoint.
30-minute break.
Say again.
No, nothing, teacher. What you said, teacher?
21.2. 21.2. Checkpoint.
Ah.
Write down. A wire is stretched between two fixed points, 0.5 meter apart. What is the frequency of the sound emitted when the wire vibrates in the fundamental mode? The speed of sound is given you. So you should be able to do that. We have learned that last week. Okay, so how to calculate this one?
F equals to VO lambda.
Yeah, how to calculate your lambda?
The lambda is the 0.50 meter lah.
Lambda is what?
0.50 meter.
No,
Oh.
you never study, that's a problem. You should be able to derive it yourself. The first loop, there's a node at the two end there. So you look on 10, there's a 0 there, there's a maximum there. Then this is only derive it. Half lambda is 0.5. Lambda is 1. That's how you calculate. You can remember the formula, use the formula. Remember it, you're not going to derive it. Okay? Describe the change in frequency of the sound emitted when the tension in the wire is increased. Okay? You should go to tell me. We have done that last week. Problem with you, you don't bother to do homework. That's why you won't progress. Then you forget everything. Then I have to scold you. Yeah? What happens if we increase the tension? You have no choice. You want progress, you have to don't give excuse that it's phobia. It's not phobia. It's just that you're lazy. You want spoon feeding. You're going to struggle when you go to university. Because university lecturer give you the lecture, and then you're supposed to go and read yourself. No more revision book. No more tuition. Right? Go to the formula. The frequency we can calculate out. Right? That's your speed. That's your the 330 hertz. Right? Go to this one. Right? V equals to square root T over mu. Okay. So your frequency is proportional to speed, right? So your frequency is proportional to your tension. Okay, from that formula, lambda is the one that we have derived, right, for the first one. So it depends on the speed. Speed depends on the tension. The frequency is proportional to root T. Okay, so you should be able to, should be able to say that the frequency as F increases, as T increases, F increases. That's all. Based on the formula. Any comment? Anything not clear? Yep. Any comment? Any question?
No, teacher, clear.
You have to do something about it. Okay, as I say, so far the problem with you is you're not putting the effort to learn. Yeah, hoping that you come for tuition, it will help you. It won't help you because tuition will just teach you and you have to learn yourself.
Mm.
I cannot learn from you. You have to overcome your phobia if you have phobia. Okay, the wire is substitute with a thicker wire of the same material. Tension in both the wire are the same. Yeah, thicker wire, what will happen? Yeah, happen to the frequency, you use a thicker wire. Right, make sure you write it down. Don't get lazy and then always ask me for recording it. You want to do your homework. Right, same thing. Right? Remember your frequency is proportional to speed. Speed is proportional to mu. Mu is your mass per unit length. Right? So it's proportional to 1 over mu. So it's same length. Right? Remember this mu is m divided by L. Same length. Frequency decreases as mu increases. Okay? Can? Can or not? Can or not? Thicker means it's heavier, lah. Right? Heavier. Thicker means heavier. That's all. So it means that your mu will increase. This one. Mass per unit length will increase. Thicker means heavier. Same length. Sorry, length also don't know how to spell. Yeah, sorry about that. Length. Okay, not anything not clear? Let's do another one and then they'll call it a day.
Yeah, become 1.5 hour already.
Yeah.
So just go on, Jeff.
Okay, let's solve another one then. Sound is produced by a stretched string. Frequency of the first harmonic. I think this one I'll let you do. I will do a closed pipe. Right? Do a closed pipe there. Okay, we'll do this one. The others you can do yourself. A vibrating tuning fork of frequency 340 Hz is held over the open end of the resonant tube, which is closed at the other end. What is the length of the air column in the tube when the vibration of the air column is fundamental mode, first overtone? Right? So draw roughly the picture. A closed pipe. Right? This is a quarter wavelength. Right? Lambda is V over F. So V is 330. You are given the fundamental frequency. So you can calculate your wavelength. V over frequency. That's your wavelength. Then either you remember or you can draw it out and derive it. This is 0. This is maximum. So it's a quarter of a wavelength. Right? So lambda 1, you calculate, put it inside there. Divide by 4, you get 0.242. Okay. Then you should be able to get the first, either you memorize it or, okay, what is the length? You calculate that. Let's go to the first overtone. Right? Frequency is the same. Wavelength is constant. Right? Because the speed is still constant. The length must change. Right? Length is 3/4 lambda 3. Okay. Derive it. So 3/4 is 0.75 times that's your wavelength. We are using the same wavelength. Right? We are not using a constant length of the tube. Right? Because we want the first overtone, we want the same tube, same frequency. So you have to make the length of the tube longer. That's all. Right? So that's why we are using the same wavelength. Right? Instead of lambda 1, we call it lambda 3. Same thing, same wavelength. Except the length is longer now. That's why we get longer length, as well. Previously, we tissue, we use the same length of the tube. So we got different wavelength. But here, this wavelength and this wavelength is the same. Right? Instead, the tube becomes longer. How will the resonant length of the air column in A be affected when the temperature decreases? Yep. Temperature decreases. Right? Must always go. Can answer me? Right? Go to the formula. As temperature decreases, speed of sound decreases, wavelength decreases. Right? Wavelength decreases, so the length is shorter. Can or not?
Can.
Right? We are basically using temperature decreases, speed decreases. Right? Speed decreases, wavelength decreases. That's all. They're just using this formula to read. And then the length becomes shorter. This length becomes shorter. Okay. If not, try the rest for your next week. If there is any no cancellation, we have a Friday class. If you want earlier, you let me know.
One earlier replacement you need.
So I will stop here. If there is any question, you ask. If not, I will stop here.
So far not.
Okay. Stop here. Have a good day. Make sure you study and do your homework. If no progress, I will always scold you in class. That's all.
You always call me just to motivate me.
Yeah, if you understand, I'm scolding you to motivate you to do something. If you want to do well, you have to put your effort. Not me, right? My effort is to teach you as well as I can.
I asked something you don't mind, Say
again.
I asked something you don't mind,
If ask, you can ask. No problem with me. I can answer you.
No. Because all the while I very phobia in physics. I never do anything. I very lazy. But then, despite all this, you still want to teach me, right?
No, after I teach you, go and do the exercise.
No, I mean, because some teachers will give up on me, but then you don't give up easily. You still think I can do it. That's why.
No, I won't run you down. Won't run you down because I see there's hope for you. Right? There's hope for you. You can do it. It's just a matter of you don't put in the effort. Won't run you down. Don't worry. Won't tell you. Don't call you stupid. You are not stupid. You are clever. It's just that you won't put the effort to learn. You need to be motivated. That's all. Maybe you are a bit slower to learn, but it takes time. It's okay. Spend more time. That's all. Okay, no? You can do it.
Okay,
It's
teacher.
not. You put effort there, then you will see the improvement. That's why I teach you very little bit by little bit, hoping you have the time to do your homework. That's how to progress. Don't go too fast. Go too fast, you get lost.
Yes, teacher.
Okay? That's why I'm going slow with you. But the problem with you is you're not putting the effort to learn. Don't worry what a teacher say you. Teachers sometimes are bad. They just run people down. Right? You can do it. It's up to you. Put in the effort. Okay? Anything
Okay,
else?
thank you so much, teacher. Have a good day.
You can do it. Make an effort. Then you see the improvement. You will be slowly.
Okay, teacher, I believe you, teacher.
Okay. Then we'll stop here.
Thank you so much, teacher.
Bye bye.
Have a good day, teacher. Bye bye. Have a good day, teacher.
Okay. Bye bye.
Bye bye.